In this video, we present Tempo, a method for efficient multi-camera 3D human pose estimation, tracking, and forecasting. The current state of the art in multi-view human pose estimation trades accuracy for efficiency. Learning-based methods rely on expensive 3D or 4D convolutional networks to produce millimeter-precise estimates, while optimization-based methods can run extremely fast but often produce inaccurate results. Furthermore, the existing state of the art does not take advantage of temporal information while estimating 3D human pose. Context from previous frames can offer valuable cues for estimating current pose, and temporal information is required for important tasks like tracking or future pose prediction. We present TEMPO, which stands for Temporal Pose Estimation. Our method efficiently aggregates temporal context while producing the most accurate pose estimates, addressing the trade-off between efficiency and accuracy. Our method has three modules. The first is the person detector. This module, following previous work, unprojects learned 2D image backbone features from each camera view into a fixed 3D volume. We obtain the dimensions of this volume using the camera input matrices. We use bilinear sampling in 3D to obtain the 3D features. From these unprojected features, we regress the body centers for each person in the scene, as well as a tight bounding box for each person. The tracking module is the next component, and it just uses a simple Kalman filter-based tracker, specifically SORT, to associate the detections of a person at time t with the previous time steps detections based on the bounding boxes for each person. This allows us to connect features computed for each person over time. At time t, we compute a pose embedding using a projection to 2D in each dimension and produce a temporal embedding by using previous features associated to that person using an RNN. We pass the output of this temporal module through a decoder to produce an estimate for the current and future pose. Here's a more detailed look at the pose estimation module. At time t, we have unprojected features in a feature volume centered at a detected person in 3 dimensions. We take the maximum along each axis to produce 3 2D embeddings, which we concatenate and pass through an encoder. We also take the previous pose features, warp them so that they are centered on the current detection, and pass all of these through a spatial GRU unit to produce a single temporal embedding. This is then passed through a decoder to produce current and future pose. Here are some sample visualizations. Our model works well across many different datasets. At the top, we have the CMU Panoptic dataset. In the middle, the Human 3.6 million dataset, and at the bottom, we have the newly collected EcoHumans dataset. Our model is able to robustly capture pose even in highly occluded scenarios. Here are some sample videos of our model's performance. In the EcoHuman scenario, it tracks effectively while also estimating pose to millimeter accuracy. In the Panoptic Studio sequence, we see that even with high numbers of people and person-to-person occlusion, our model is able to robustly estimate and track 3D pose. Here are some quantitative results. In the first table, we see that Tempo achieves state-of-the-art MPJPE on the CMU Panoptic Studio dataset across multiple resolutions and backbones. It is also comparable to the state-of-the-art on the Shelf and Campus datasets, and we achieve state-of-the-art forecasting and performance and comparable tracking performance using just simple and efficient components, with our whole system running at the same speed as the fastest methods. Thank you for watching, and please visit our website to learn more about our method.